She said, I'm Seth Kenner. Jason's over there. He'll just be here for a little bit. So, like you said, it's a Scenario Application Manager. So I'll be, trying to go through the 6 questions that we're addressed and a few other things, and I'll probably be jumping back and forth between the presentation and doing a little demo and looking at some other stuff. But starting out with that 10-year cycle, Chuck's great presentation. You might be feeling like that guy in the upper right-hand corner, thinking about HSPF. I've been working with HSPF for a while, and that's kind of how I felt when I started. And then I started developing tools like SAM, and then it became like the guy in the lower left-hand corner. Just kind of one click, and once you understand the science, it can be that way. And so in SAM, we built our expertise into that. So you're using HSPF expertise when you're using it. So like Chuck said, HSPF has mainly been used for kind of the monitoring and assessment and water resource characterization, kind of in filling the gaps in the monitoring and identifying and quantifying pollutant sources. And so when we bring in SAM, it really is still using HSPF, but it allows for easier and more widespread application of HSPF to the rest of the 10-year cycle in doing estimating load reduction, simulating and evaluating management scenarios, evaluating downstream impacts of those management scenarios, and also cost effectiveness. And then, like you said, they're going to update these models, and so it's really going to be an easy task to update those models in SAM. And then also, if you do monitoring on your BMPs, you can update the efficiencies and information from the BMPs that are used in SAM. So, like Chuck said, it's funded by the MPCA to expand the use of HSPF to the planners and people that are less technically familiar with HSPF and how to use its files, because it can be quite complicated, as you saw in Chuck's presentation. And so there's 3 primary components. There's the HSPF model, and then there's the task tool, we call it, which is a preprocessor. And that requires still some HSPF knowledge, but then that creates the input to SAM. And I'll talk a little bit about that further. And you've already kind of heard about the development of HSPF applications. So here's kind of a diagram of how we see the flow of SAM with HSPF working. And so you see, from Chuck's presentation, the breadth of information needed to build these models. And so the HSPF expert takes those and builds these models at a Huck-8 scale. And so we built path tools that someone who's more practiced with HSPF still understands kind of what the ideas mean. They don't need to know how to manipulate HSPF files. The path will do that. But just to understand what went into the model, where the sources are, and everything like that, they'll take those Huck-8s, and then we're creating those to create basically a project that represents a Huck-6 watershed, which could represent numerous Huck-8 HSPF models. And so from there, someone else can use the path tool or the same person and load that Huck-6 application and create SAM projects that represent those Huck-8 HSPF models. They can represent subsets of those Huck-8 or combinations, so large scale. So the entire Huck-6 could be represented with a SAM project. And then those will be used by someone with minimal experience to apply and create solutions for their watershed using the HSPF model. And so the path inputs are basically HSPF model files, which will include the observed data that are used to calibrate it, but then shape files representing the subbasins, which you'll see how that's used in SAM, and then also a scheme that basically tells you what in the model represents what in the real world. So there's a lot of different functionalities. The path tool translates HSPF files. It links the shape files to the model domain. You can map the HSPF sources dynamically, and then you can do different SAM application options, like before, create a small one, a large one, and then simulate whatever pollutants you want. And then you can use it to review and validate the model results, and also extract model results. And so then in the SAM, the input is basically the SAM project file that was created by the PATH preprocessor, and then a built-in DMP database, but that's also editable and customizable as you use SAM. So in SAM, there's the GIS mapping, which allows you to select the basins that you want to look at to relate the model domain to the real world in GIS. You can look at existing conditions before you run any scenarios, and then you can develop scenarios, do analysis and reporting. Now, we're still developing SAM, so there's some functionality that I won't be demoing. I'm going to show some screenshots of the progress, but it's still in development. So these are kind of the three primary areas that we see SAM being the most useful. So I'm going to jump into the demo. So starting with the PATH project. This is kind of what it looks like. And you basically just can start loading up the input file for HSPF. And what it does is it just goes in and starts, it processes all the information needed, and you don't really, all you have to do is know where the HSPF file is. It's pretty simple. So now all the information it needs is processed. It's just built in. We jump to the source. You can see that it populated this table. It identified all the different sources that are being represented by that model. And so they're in HSPF lingo, and that's where you kind of got to be familiar with HSPF in this part of the process to understand what these mean. What is it cropland? Is it a point source? Things like that. And so you need to be somewhat familiar with that. But you can load multiple models. So that was one model representing Huckgate. And then I'm going to load up one more here just to show you how they can link automatically. So I loaded two models. You can see it automatically was able to determine, where in this model flows into this model. So they're essentially linked. So if you were to load this in SAM and run a scenario on one model, even though they're not built into the same HSPF model, you will see the impact flowing through the other model. And so then you load up the shapefile info to link to, I'm not going to do this, I don't have time, but you basically just link attributing your shapefile to the IDs from the model. And so in here is where you can kind of interactively build your source scheme, or you can build it in a text file, save it, load it in different ways. So here you would enter information that represented a source. I'm just going to load one up to show you what it means like to have a full scheme set up. Taking a little bit to load it in. So now you see there's maybe 15 lines to make a scheme, but we've given a kind of a source identifier to each of these sources within it, whether it's point source, web, and you can So like all of them, I just call them point sources in this demo one, but you could give them their individual names, and then after you run it, we be able to look at the loading from each of these unique ones and categorize them in this way. So I'm going to open a project that's already been run. It takes about the time you need to run the model, and then a little bit of processing time after, which is about, for large two models, probably 15-20 minutes, so we don't have time for that, obviously. So I'll just load one up. And so while this is loading, let's show kind of some screenshots of stuff that's not in the demo right now. But so this is kind of the validation where there's a loader to load observed data through kind of a couple questions, whether it's row or column format, and then you link it to the reaches in the models, so the data is being compared to the right simulated results, and then you can look at, this is just showing a flow duration curve, which is a common plot we look at when we're calibrating, and also the stats behind that, which you saw some of those in Chuck's presentation and are common throughout calibration. And so this is in there so that when someone is processing an HSPF model, they can look at the quality, and determine whether it's, how useful it's going to be for someone. All right, so it's loaded up. This configuration allows you to set what you want in your SAM application. So when you load up your past project, it's going to be, when it's fully statewide application, it's going to have all the files for the HUC6, and then you can come in here and you'll be able to select kind of the endpoint of everything upstream that you want in your SAM application. You can select the constituents, have them all. You can only run some of them if you want, but then we can export results in this as far as daily time series, concentrations, loads, source loading rates per reach. So it's easy to once you have this, you can grab the inputs needed for your bathtub model really quickly. And then I showed you the validation tool. And now I'm going to jump into the SAM application. I'll load up a project file that was created by the past. So you can see the GIS window and some pretty basic GIS functionality here. Not going to demo it all, but in here you can do a lot of the same analysis you could do in the past, but we have added, you can do plots and maps, and the maps kind of where we get some interesting data. And so if you haven't run any scenarios, you'll probably just see the base condition right here initially after the path creates the file. I have some scenarios run already, so we can look at some analysis with that. But so initially, you would probably look at some base data. I'm going to plot kind of a base and loading rate for total phosphorus in the map. And what that does is basically creates a loading rate for each sub-watershed, so you can plot it on the map. It adds it to the GIS component, and so you can do some quick symbolization. So now we can see and look in here and see some areas pop out as to higher source loading rates. So we see people coming here, and we can do this really quick using model results, and we can even just jump into building a scenario. And so you see your base results, and you see some areas of concern, and you can start running some scenarios by building into those. So We have a step-by-step approach kind of set up where you first select the basin you want to see, and you can look at some quick data here on what the issues of concern are for your selected basins. And obviously it's cropland for this area. And then we can jump to step 2, which is, do we want to add some land use change? So we can add any kind of land use change. And then step 3 is where we would add BMPs. And so right now, here's a list of the BMPs. It's expanded from this version, and we're continually expanding as we test it and use it in more and more pilot watersheds. And so it's pretty easy to update the BMP database as long as we have data. And I'll go into a little more detail of the database a little later. And so we can edit costs that are associated with BMPs and then participation levels. There's a suitability built in that's based on the NBMP and PBMP tools, and I'll discuss that a little bit later. But that can be applied or not. And so you would edit those, and then you can come in and edit efficiencies. We have multiple sources for getting efficiencies for the main 4 parameters that we are using them for. And then we can also change efficiencies for surface, interflow, and groundwater. And so once we have those, we can add those practices and create a scenario. And there's point sources we can add if there were any in these watersheds. We can add a point source, or we can cap concentrations, numerous things, and do things with other point sources. For example, if we had a watershed that we weren't modeling an upstream watershed, we just had a boundary condition, we could add something in here that represented something where we know upstream is meeting the standard that we want to have. And so we can set that here, run that scenario, and then we can start improving our watershed. So we're not trying to fix the problem, that was created upstream. Do things like that with that. Then we kind of design our scenario. So step 1 through 5 you would repeat for each set of selected sub-watersheds. So you can come in and do one watershed at a time, doing customized BMPs, or do large-scale application of BMPs. And so once you do that, you can create the scenario, or you can add a climate change. Right now there's 3 options: a mild, moderate, severe. These are kind of the specifications of what happens, but it's not all the details of what happens in the climate change. There's a little more complexity to how that gets applied to the time series, meteorological inputs, because there's adjustments to temperature differently if it's in the summer or winter. And then there's adjustments to ET that happen also. So once you kind of design the scenario, you can run it. Once you've run it, it'll show up in here, and you can always come back and see what went into that scenario. And then in here we can analyze it. So if I wanted to look at, say, the reach loading, maybe the leach load % reduction from our base scenario for this scenario, and in the map, let's look at some phosphorus and run that and plot it. You can see we implemented BMPs up here, but you can see the impact that those BMPs have downstream, because it's stimulating the fate and transport of the pollutant. And then we can also look at cost along with that. And so if I normalize by cost, we're looking at, say, a % reduction per dollar that we're getting. Let's compare and see what we get, and you'll see a difference in the impact. And you see a couple of ours that stand out where we're getting a larger cost effectiveness for the BMPs you're using. And so that kind of fits the design. And then later, we're developing a targeting. Just a quick screenshot, but basically you would, to target, you would build all the options, all the possible options that you would want to include in the targeting in this design window. And then there would be many other options to constrain your optimization. As far as what reaches you want to look at, you can add, I want to be, in these reaches, I want to be less than 1 milligram per liter total phosphorus, but I don't want to spend more than, $1 million or something like that. You can add all these, and you can add multiple constituents. You can add different reaches, and then when you run it, it will go through and use your design options. You can click to use all the possible options if you want, but you can also limit it to certain ones in the design window and use those, and then it will go through and based on your constraints, try to get you the best scenario for that area for the cost. So I went through most of that. So I'm just going to jump to the BMP database. So our methodology is, you kind of saw this as I was demoing, but we're mainly looking at efficiencies for slow sediment, nitrogen, and phosphorus. And you can have different efficiencies for surface, inner flow, and groundwater. And we also look at the in-stream responses to upstream reduction. And then also includes cost per treated unit per year. And then there's customizable areas, efficiencies, and costs, so you can edit those. And the references we have right now are from Minnesota Ag BMP Handbook, Yellow Medicine Maps for the pilot watershed where we did sampling, and then MBMP and PBMP tools, and we're currently developing some urban and in-stream and forestry BMP. And so a key component is the suitability, which is based on the NBMP and PBMP tools, where for each BMP and each puck, we have an estimate of the suitability of the certain land use that those BMPs are applied to, and how much that they can be applied. And so it limits it. So if you have a BMP that, say, is really only used for corn, then it will limit it to the amount of corn in that watershed. And it can get more complicated than that, and I'm sure Dave might talk about that a little bit. But and then we basically link the NBMP and PBMP tool BMPs to NRCS BMPs, and then use the EQIP 2016 EQIP cost database. And so for a pilot application, we worked with the Yellow Medicine on a one watershed, one plan, where we were working with them kind of before the HSPF model, and especially before SAM was really usable. And so they used HSPF results somewhat when they could, but they kind of developed a plan initially, and they set goals for their watershed. And so then recently we went in there and we had SAM fairly functional, and so we went in and trained them in half a day, and then the second half of the day we grouped them in groups, looking at the different areas of concern, and they had goals for each of those watersheds, and they used SAM to see if they could meet those goals with the plan that they had developed. And so, and based on that, I think they were able to adjust their plans and improve their direction on where they need to go to improve their watershed. So as we roll out, I talked about this a little bit, but it'll basically be touch fix past projects on likely MPCA server, And someone with, a little bit of HSPF knowledge can use the path tool. Someone who wants to use SAM would request, I want this watershed, a SAM project for this watershed that hits this outlet, and they can go and set the variables, click, run it, probably, 20, 30 minutes to run it, hand it off to you, and you can start running with scenarios, getting results for the HSPF model. So advantages and limitations. Obviously, advantages are non-HSPF experts, being able to leverage the power of the complex model. And then it's obviously linked to a calibrated model, but also the large and small scale. So you can have, HUC6, look at the HUC6 level, even though there are multiple HSPF models, or even a subset of an HSPF model. And customizable BMPs, cost efficiencies, and the suitability, and then also the quick updates. Because we're going through the 10-year cycle, they want to update. It'll be easy to plug those back into the project and update the results. And limitations, it's obviously limited by what you represent in the HSPF model, the quality of the HSPF model, and then it is a desktop application, which if you don't like to be online, that's fine. But potentially someday it may be able to move online, which could create some advantages. But time series is only stored in a daily time step due to the limits of space and expecting your computers to be able to handle a lot of data is difficult to do and could run into issues. Now, even though it's stored a daily time step, the model still runs at an hourly time step. We still do the same processes at the hourly level. And especially for DO, we output the min and max, and so we get the flux and all that information is available. So you may not get the hourly every value of DO, but you'll get the min and the max and the flux, which is mostly used to compare and try to meet the standards. I think that's it.